Hello everyone. So we are jumping into topic 1.3, and so we have elemental composition of pure substances, and this includes like visually, if we could zoom in, like what would we see as their composition, and then also formula wise, like what subscripts do we have, what ratios do we have between atoms. So that's what is encompassed in here, and there are calculations for those as well, like how do we calculate the formula. So let's start with a visual representation of this. So matter broadly can be broken up into two different categories: a pure substance and then mixtures of those pure substances. So let's understand this first, and then we'll see how these things can be mixed. The first is when it's an element, okay? Let's break this in half, and just know that I'm giving you two different examples of what an element sample can be. They're not a mixture, okay? So this is not like in the same container. I'm giving you two completely separate examples. So let's do like example 1 and example 2. These things are not in the same container. So one example of this, and this is true anytime it's an element, there's only one type of atom in the sample. Okay, so like let's say that the type of atom was oxygen. Okay, and so we could have, and actually let's do a different one. Let's do carbon's a common one. Let's do carbon. And so if we just have these atoms of carbon, okay, and all of those are the same. Sorry, I didn't draw them like quite equal in scale, but there's only carbon atoms, and that is it in there, then that would be an element. They don't have to be separate like this though, and that's where our example number 2 comes in. What if instead of carbon this time we have oxygen, but oxygen when we find it out in nature tends to be as O2. Sometimes O3, which is ozone, and this would also work in this category, but what if it was O2? That's our most common. So like that'll be our O2. Both of those atoms are oxygen. And if this sample that I'm looking at, I scoop it out of nature, and that's what I see, that everything in the sample that I'm looking at is only oxygen atoms. Yes, they are chemically combined into a molecule, but they are oxygen, 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 oxygen. That is a pure substance, and it would be in the element category. Okay, great. Now let's talk about compounds. Okay? So compounds contain more than one type of atom, where element only contains one type of atom. But the structure that they're making, usually a molecule, that is what's repeated over and over. So what if I go out in nature, I grab a sample, I grab a scoop of atoms, or really just like molecules, whatever. I go get a sample of matter out of nature, and then I analyze it, and what I see is carbon dioxide, a CO2. Okay, so then, but that's the only thing that is there. Is over and over again, it's just CO2 in my sample. That is still a pure substance. There's more than one type of element involved, but the only thing that's in this sample is carbon dioxide, is CO2. Okay? Where, here's my example 1. This would just be carbon, and then example 2 would be O2, but it's only oxygen. All right, so those are our pure substances. We have elements, and then we have compounds. Now, when we take these pure substances and we mix them together, meaning not chemically combine them, not forming bonds to make molecules, but we put them in the same space, then we get a mixture. Like, what if we take let's do a different one. What if I take neon atoms. Neon, 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 neon. Okay, so here's neon atoms. Now before I mix it with something else, this would just be an element. I can either mix it with a different element or a compound. And so what if we also happen to have water vapor in there, like an H2O? I'm going to color in those, and we'll say those are hydrogens, and then that one's oxygen. And so then what if we also have water molecules in there? Now, do you see how the water is kind of like evenly, more or less, spread through the neon? They're not chemically combined. That's what makes it a mixture. Like if I were to write this out, it's like neon, but then there's also H2O in there. Okay? Like both of those things are in there, but they're not chemically combined into a new molecule. And that there have even distribution throughout. They're not gathered in one spot. Then that would be a homogeneous mixture. Now, if I zoom out of this, I'm not going to be able to see the difference here. Meaning, like, let's say that I have a glass of water and Gatorade powder, and I pour that Gatorade powder into the water, and then I mix it all up. Before I mixed it, it would be heterogeneous, but after I mixed it and all the Gatorade is evenly mixed throughout that water, and now I can't really see the difference between the water and the powder, even though they're not chemically combining, that would be a homogeneous mixture. Okay? But what if the water was like gathered at the bottom? Okay, there's the water. And then it wasn't evenly mixed with the neon, like the neon is floating up above it. Neon, neon, again, sorry, I'm not doing them all the same size, neon. And so what if my neon was floating up above? They are in the same container. They're placed in the same space, but they're not evenly distributing between each other, and so that would be a heterogeneous mixture. In a heterogeneous mixture, pretty commonly we can see the clumps of the different things. It's like I can see the clump of Gatorade powder before I mix it into the water. That'd be heterogeneous. If I mix peas with beans, that is, even if the peas are evenly distributed throughout the beans, the atoms, there's a big clumps of like the atoms composing the beans and then the atoms composing the peas, and they're all kind of clumped together. I, as a human, can visually see that's where the peas are, that's where the bean is, right? And that would be a heterogeneous mixture. Just like a salad, I can see all the stuff in the salad, and so that, and I can see that they're not all the same things, and so that would be heterogeneous. Okay, so we're going to come back to this as our reminder for class time. Let's keep going. So there's a difference between an empirical formula and a molecular formula. An empirical formula tells us the lowest whole number ratio. Look, it says it right there. That's the lowest whole number ratio of these elements inside of the item, inside of the compound, whether it be a molecule or an ionic compound. Where a molecular formula tells you the exact number of atoms in the item. The exact number and type of atoms in the molecule or ionic compound, okay? So this molecule, C4H10, if I were to get a C4H10 molecule, it would have 4 carbons and 10 hydrogens in it. If I were to figure out what the empirical formula is for this sample of these molecules, my ratio is not, the lowest whole number ratio is not 4 to 10, okay? Like, here's our 4 carbons, 10 hydrogens. That is the correct ratio, but it's not the lowest whole number ratio. And so you should think, what's a number I can divide both of these by that it still stays a whole number? And one number that I could divide both of them by is 2. And so then 4 divided by 2 would be 2. 10 divided by 2 would be 5. And then I go, is there any other number that I can divide both of these by and they still stay whole numbers? And when the answer is no, then we found that lowest whole number ratio, right? So the lowest whole number ratio for the carbon to the hydrogen in the sample of this molecule would be 2 carbons to 5 hydrogens, and that's what we see here. Empirical formula is not a very helpful thing. Yes, it tells us the ratio, which is lovely, but we won't know what the actual molecule is. The reason why we even have this concept is that mathematically we get to this location first, and then we're able to figure out what the molecular formula is after the empirical. And so that's why we have it. It's a stepping stone on our way to figuring out what the molecular formula is. Okay, so let me give you an example of this. If the percent composition of iron oxide is 69.94% iron and 30.06% oxygen, what is the empirical formula? Okay, so let's make an assumption here, because they didn't quite say, but if it doesn't say, then we're going to assume that these percentages are masses, like that of the total mass involved, 69.94% of the mass is iron and 30.06% is oxygen. If it's something other than that, like if it's a percentage for moles or anything else, then they have to tell us in the problem. But if they don't tell us, then we can assume that it's mass. Here's my first trick for you. Anytime that I see percentages, I'm going to assume that my sample of this iron oxide, how much iron to how much oxygen, whatever it is, my sample of this is going to be 100 grams. I'm making that assumption. Like, it is going to be easiest for me if I go get a sample of this that is 100 grams. And the reason why it's nice for that to be 100 grams is because then we get such an easy translation to 100% of the sample. So if I have 100 grams of this thing and 69.94% of it is iron, that means that in this 100 gram sample, 69.94 grams of that 100 is iron. And then the other thing that I know is if I have a 100 gram sample, and that is how much of it is iron, then the remainder has to be oxygen. So they didn't have to tell us this number. Like if they tell us it's only iron and it's only oxygen, and this percentage of it is iron, then whatever is remaining, the remaining percentage is the oxygen. But luckily it gave us that number. And so we know that of this 100 gram sample, 30.06 grams are oxygen atoms. Okay, great. Now, these subscripts, kind of like the coefficients, are like moles. Meaning, like, let's do, what if I had, let's draw a little box so we can keep items separate. What if I have H2O? Okay. And we know there's a coefficient of 1 in front of this. We just don't tend to write it down. And we also know that there's a subscript of 1 with the oxygen. And so 1 mole of H2O could turn into 2 moles of H plus 1 mole of O. Like in its simplest form, just the individual atoms. That 1 H2O can break into 2 hydrogens and 1 oxygen. But we've been playing with this idea that coefficients can also represent moles. So this is like for every 1 mole of H2O, we could break it apart into 2 moles of hydrogen and 1 mole of oxygen. So what's cool is now these subscripts can also represent moles. Moles are our bridge, like it's how we get from point A to point B. And so right now we're going from percentage to empirical formula. And our bridge to getting there is moles. So if I have 69.94 grams of iron, let's figure out how many moles of iron that's going to be. And then I want to do the exact same thing for the oxygen. Here's my grams of oxygen. I want to end with moles of oxygen. Okay? So I'm going to go pull out your calculator. I'm going to grab a periodic table. I want to make sure I give you the exact numbers that are on your reference sheet. Okay. So, reminder that when you look at your periodic table and the number that we see there, not the atomic number, that's the number of protons, but below the symbol, that is the mass number. It's how many grams there are in 1 mole. So I find iron, it's got an atomic number of 26, and it's got a mass of 55.85. That's how many grams there are in 1 mole of iron. And then for oxygen, we have 16 grams per mole. Okay, lovely. So we're going to go from grams to moles on this. So I'm going to take 69.94, divide it by 55.85, and I'm getting a long number with a decimal, 1.25, etc. Okay, I'm not rounding yet because it's not my final answer, but I am writing enough digits here that I can remember which number this is, so I can maybe throw a 2 in there as well. And then I'm going to do the same thing here, 30.06 divided by 16, and I get 1.878, etc. This is my moles of iron. This is my moles of oxygen. Now, do you remember when I told you my trick whenever it's asking for ratios? Whenever we were wanting ratios of numbers, the easiest way to figure this out is look at which number is the smallest. In this case, it's the iron, right? There's my moles of iron. There's my moles of oxygen. And take all of the numbers that are involved in this ratio, and luckily we only have 2 numbers that are involved in this ratio, here and here, and divide them by the smallest number. So I'm going to divide both of these by our smallest amount of moles, 1.252. So if I take 1.252 and I divide it by 1.252, etc., that is going to equal 1. And then this 1.878 number, and I divide it by the 1.25 number. Notice that I'm grabbing the longer numbers in my calculator, and I get roughly 1.5, 1.500, 1.5. Okay, so the ratio between iron and oxygen for my moles, my subscripts here, is a 1 to a 1.5. But we want whole numbers, not fractions. So what can I multiply both of these by so that they are a whole number? And the easiest, when it's a 0.5, we're going to double these things. So for every 2 moles of iron, we're going to have 3 moles of oxygen. And there's my empirical formula, Fe2O3. Okay, one more time. If they give you percentages, assume that you have a 100-gram sample. The best reason for doing that is because now these percentages all of a sudden become grams. Because of the 100 grams, 69.94 grams are iron, and 30.06 grams are oxygen. Our subscripts as well as our coefficients can represent moles. So I'm going to go from grams to moles of the individual elements. I then had my number of moles, and this is the right ratio. The ratio from iron to oxygen in moles in these subscripts is 1.25 to 1.878, but we want whole numbers. And my trick whenever we're trying to figure out whole number ratios is look at all the numbers involved, figure out which one's the smallest, and then divide every single number by that smallest. And that gets us really close, if not to our whole number ratio. So that was changing this to a 1, and that changed this to roughly a 1.5. Because this wasn't a whole number, I multiplied both of them by 2, and that allowed for our amount of moles to be a whole number for iron and for oxygen. And so our ratio to iron and oxygen was 2 iron to every 3 moles of oxygen. And so there's our empirical formula. Okay. Now, if we are not given percentages, just know that our goal is to figure out the moles of each individual element. Okay, like whenever it's asking for empirical formula, okay, so everyone, empirical formula, whenever you see that on a question, your mind should go to moles of each element. Okay, hey, figure out the empirical formula for this thing. Oh, you should be, first step, I need to figure out the moles of each of the elements involved. So in a sample of a compound that contains only the elements carbon, hydrogen, and nitrogen, is completely burned in O2, but see how oxygen's not part of this, but it was burned in O2, to produce 44 grams of CO2. All right, so I have, do this first one here. I have a 44 grams of CO2. Now, I don't want to have grams of CO2. I want moles of each element, and the element that's contained in there is the carbon. So I have grams of CO2. I want to end with moles of carbon. How would I do that? Well, I can go from grams of CO2 to moles of CO2. Okay, and then my last step is going to go moles of CO2 to moles of just carbon. I'll help you do this one here in a second. So reminder, whenever I'm figuring out how many grams there are in a mole, I'm going to look at my periodic table. And on the periodic table, it says that carbon is 12.01. That's how many grams there are in 1 mole of carbon. And there's 1 carbon inside the CO2 molecule. But there's also 2 oxygens. And so when I look at my periodic table, I see that there's 16 grams for every mole of oxygen, but there's 2 of those oxygens. So adding all that up together tells me how many grams there are in 1 mole of that individual item. So I have 44.01 grams of CO2 for every mole of CO2. All right, lovely. Moles over moles. Now, I don't have this great balanced equation right now, but I can show you a really cool trick. What if we have 1 mole of CO2? And I want to know how many moles of carbon there is in there. We could also figure out the moles of oxygen. Great. But I'm just worried about the carbon right now. So 1 CO2 contains only 1 carbon atom. So that means for every mole of CO2, we only have 1 mole of carbon. If it was oxygen, because there's 2 oxygens in there, for every 1 mole of CO2, there's 2 moles of oxygen atoms. but this is just a 1 to 1. All right, great. So, sorry, I didn't leave a lot of space, so I'm just trying to sneak it all in here, careful. So then 44.0 times by 1 divided by 44.01 grams times by 1, it equals pretty much 1 mole of carbon. All right, great. Let's keep going. What about hydrogen? There was 45.0 grams of H2O. Okay, so we have 45 grams of H2O. And our goal is moles of each of these elements. And I now know moles of carbon, so let's figure out moles of hydrogen. So I'm going to go from grams of water to moles of water, and then moles of water to just moles of the individual element, hydrogen. I'm going to go to my periodic table anytime it's moles over grams or grams over moles. And on your periodic table, it says that hydrogen is 1.008, but it's an H2O. So there's 2 hydrogens and 1 oxygen. So for every mole of water, it is 18.016 grams of water. Okay, now, whenever I have moles over moles and I don't have a balanced equation, I like to put 1 with the more complicated item. 1 mole of H2O. And it's like, okay, then what would it be for the hydrogen specifically? And we go, well, if I have 1 water molecule, there's 2 hydrogens in there. Yes, there's also 1 oxygen, but I'm less worried about that. So every 1 mole of H2O contains 2 moles of hydrogen. All right, so 45 times by 1 times by 2 divided by this 18 number gives me 4.995, or in this case, roughly 4.99 moles of hydrogen. It then goes on to say, and some NO2. I'm like, oh no, but wait, it's multiple choice. So I bet I can figure it out with only these 2 numbers. So the last thing I do to find ratios is I divide the numbers that I'm trying to get the ratio of by the smallest, but guess what? The smallest is 1. So 1 divided by 1 would be 1, and roughly 5 divided by 1 would be 5. So my formula is C1H5N something, but B is my only answer that has the correct ratio of carbon to hydrogen. Okay, lovely. All right, I'm gonna do one more example, and then we'll have this wrapped up. Actually, yeah, we're gonna skip that one. Yes, okay. I want us to do A right now, and then I'll help you do the last part of it when we get into class. So, determine the molecular formula. We need to start with the empirical first, okay? And then we can get to molecular after we do the empirical. And when we see empirical, we go, okay, I need the moles of each element. And there's carbon and there's hydrogen. Carbon and hydrogen, that's it. Okay? Oh, I see percentages. So let's assume that there's a 100-gram sample. That would mean that I have 92.3 grams of carbon in this 100-gram sample, and I have 7.7 grams of hydrogen in this sample. And I'm going to go grams of carbon to moles of carbon and grams of hydrogen to moles of hydrogen. And when I look at my periodic table, I see that there's 12.01 grams per mole for the carbon and 1.008 grams per mole for the hydrogens. 92.3 divided by 12.01, 7.685 moles of carbon, and then 7.7 divided by 1.008, we get 7.638 moles of hydrogen. Okay, you might be able to see it already. Maybe, maybe not. What is the ratio between the carbon and the hydrogen? Well, we can use my trick where we say, find, of the numbers I'm trying to get the ratios between, find which one is the smallest. This one's a little bit smaller, and we divide both of them by that small number. But guess what? When I plug this in, I'm going to get really close to roughly 1. It'll be a little bit above 1, but really close to 1, and then I'm going to get 1. And so the ratio between the moles of carbon and moles of hydrogen is a 1-to-1. So we get a C1H1, and that's my empirical. Okay, great. When we get to class, I'll show you how to then take that and turn it into the molecular. See you.